Hello, my name is Gil Carlson. I'm Director of Technical Services for ITT Fluid Handling Division. And we shall be discussing today one of the most misunderstood subjects in pumping, NPSH, which really means not pumping so hot, despite what you've heard previously. Of course, NPSH means net positive suction head, and defines the solution to some particular problems having to do with pumping. So let's describe those problems, and we shall describe also the solution to the problem, based not on formulas, but rather on conceptual ideas, as must have been developed when our first engineer, many years ago, developed cavitational problems and the solution to those problems in terms of concept. So let's define the problem. The problem is this: we can have a pump, and that pump can have a pressure available at the pump suction flange over and above the liquid vapor boiling point. So it would appear that the pump should work satisfactorily. However, when the pump starts, a pressure drop occurs from the pump suction flange to the inside of the pump. And this pressure drop occurs because of velocity head increases, because of turbulence within the pump, and other characteristics that lead to a pressure drop from the suction flange to the inside of the pump. Now, should that pressure drop exceed the pressure available at the pump suction flange over and above the liquid vapor boiling point, we will flash into steam or vapor inside the pump. Bubbles will be formed, and those bubbles will pass through the pump from the low pressure area to the higher pressure area available at the exit of the impeller. Now, the bubbles will collapse then as they introduce themselves into the high pressure area, and will collapse with a great deal of force against the impeller, causing erosion of the impeller and also causing problems that have to do with flow through the pump. The pump is expected to flow water or another liquid. It is not expected to flow a combination of water and vapor. If a water vapor condition occurs during pumping, flow capacity will be considerably reduced, and the objectives of the pumping application will not be met. The fact of cavitation will shake and rattle the pump impeller, can ruin pump bearings, can attack the seals in such a way as to cause a very shortened life on those seals, because the seals can be operating, the mechanical seals, in such a way that the seals are running dry, leading to a very short life on the seals themselves. So let's define again the problem. We have a pressure drop from the pump suction to the inside of the pump. If that pressure drop exceeds the pressure available at the suction flange over and above the liquid boiling point, we will flash inside the pump, causing the problems described. Now then, required NPSH is simply a statement of the pressure drop occurring from the suction of the pump to the inside of the pump during operation. So let's remember that required NPSH is a measure of the pump pressure drop. Now, how is this pressure drop illustrated? The pressure drop is illustrated on the pump curve by a separate curve, which is called the NPSH curve. It's a required NPSH, and illustrates that similar to pressure drop through a valve that of a fixed size, that pressure drop will increase as flow increases. The point is this then, that we should operate the pump in such a way that the required NPSH is less than the available pressure at the pump suction flange over and above the liquid flash point and or the, which is called available NPSH. In some cases, engineers select pumps in such a way that they will select at times a pump that will flow the required flow rate, but is a small pump. It has been defined after many years of study that a small pump costs less than a large pump. That small pump, however, operating at the same flow rate as a pump selected to the mid-area of the curve, will have a much higher required NPSH or pressure drop because the small pump has a smaller eye. Its velocities are much higher then, and we can expect that potential troubles for that small pump operating in the system. Now, given the considerations then of required NPSH, what is the conceptual idea behind the application of NPSH? And the conceptual idea, developed many years ago, is very simple. So let's illustrate that. Supposing we had a pump, and that pump is pumping water at sea level at a temperature of 212 degrees Fahrenheit. And we know that for this condition, our flash point is 0 psig. Now we know after evaluation of this pumping system that a gauge mounted at the pump suction flange would register 5 psig. This is by evaluation of the piping plans. So we would then have an available NPSH, or pressure available at the pump suction flange, of 5 psi over and above the liquid flash point. Supposing now, however, we have selected a small pump, and that small pump has a pressure drop, required NPSH, of 10 psi. This would then mean that we are below the flash point of the liquid being pumped. The liquid would flash, cavitate, and we would have great troubles in terms of operation of that pump. On the other hand, let's take the same pump, or the same condition. We have 5 psi available again at the pump suction flange, but we select a pump which has only 2.5 psi as pressure drop. We would then have plus 2.5 psi over and above the liquid flash point. This illustrates the basic conceptual idea behind NPSH evaluation and illustrates the simple concept involved. Now then, you may very well ask the question, if the concept is so simple, how does it manage to get so loused up in terms of application? And the answer to that has to do with the meaning of the pump curve. The pump curve has a statement of foot head in terms of the energy head available for that pump. Now, foot head really means foot-pounds of energy per pound of liquid being pumped. The important thing is this, that a pound of water at 60 degrees weighs exactly as much as a pound of water at 200 degrees, or indeed as a pound of water at 300 degrees, or, carrying it a step further, as much as a pound of liquefied feather. What we are saying is this, that pound per pound is canceled, but the original meaning must be understood, which finally states that the pump capacity curve is unaffected by water temperature and or by density, and the NPSH curve is also generalized in terms of the liquid being passed through that pump, except as it may be affected by viscosity. Considering this, then, if we are going to use the basic concept that of, as previously illustrated, of PSI, and convert this to foot head, and we are interested in the available pressure at the pump suction flange over and above the liquid pressure, and convert this to feet head, we must then run into a great many abstractions, which have to do with atmospheric pressure expressed in terms of foot fluid head and a great many other complications. Now, this is what has caused the trouble in terms of NPSH evaluation. But let's consider what can be done, because we can take the simple conceptual idea and convert this into a very simple approach having to do simply with your determination of the pump suction flange pressure. So let's go through a very simple system in this manner. Can take a cooling tower example. And in that cooling tower, we're going to have a water level. We're going to pump out of that tower into a pump suction. And what we will want to determine is this, simply the pressure available at the pump suction flange when the pump is in operation. Now, for this circumstance, we'll consider that this tower is at sea level and registers 0 psig. We have, for this example, 2.3 feet of available static pressure, which is going to register, if we were to put a gauge at this point, as plus 1 psi, because 2.3 is equal to 1 psi. Now, when the pump starts, we are going to have a flow pressure drop in the pump suction piping of 4.6 feet for this particular example. And that is going to register then as a negative 2 psi. So we will finally wind up then with a pressure available at the pump suction flange of a negative 1. Now, you may wonder as to why we don't take into account velocity head differences in that pump suction flange. But if we were to do so, we would mess up the whole situation. We would only take into account velocity head considerations when we're evaluating a pump system in actual operation. When we evaluate for the purpose of NPSH evaluation, we do not take into account velocity head changes. So we have then established a -1 psi G as available at the pump suction flange. Now then, to utilize that pressure available at the pump suction flange, we have developed a chart. And that chart is developed in this manner. We establish at the base the pressure available at the pump suction flange. In this case, a -1 psi. And we have plotted against that the pressures for various liquids at absolute pressures in such a way that the absolute pressures relate to those numbers that are usually used for vapor pressure determination for the liquid under various temperatures. This means the chart is available for and usable for any liquid at any temperature, providing we know the vapor flash point. So these slanted lines then are vapor flash point lines for any particular liquid. We have also plotted on this chart the water temperatures corresponding to the vapor pressure boiling points for water. So we would then take a straight rule, establish this at -1, proceed up to, in this case, 85 degrees for the water temperature being used for a cooling tower and passing through the pump. We would take that particular point and establish again with a rule a corresponding line horizontally to intersection with the specific gravity of the liquid being pumped. In this case, we would find that we would have an available NPSH of slightly over 30 feet. Now then, given this consideration, all that we have to do is to select a pump which has a required NPSH of less than the available NPSH shown on this chart. We should provide, of course, some safety factor in terms of selection, because if the pump does deviate from the selected point, that might be illustrated here. We have a selection point at this point, but as will be illustrated later in terms of power application, if our pumping point is actually farther out in the curve, we will, of course, establish a higher required NPSH and could run into difficulties because of slippage of the pumping point. So many times we will need a safety factor. But given that we have precise determination of all the considerations given for the pumping of the system, we could use any pump that has a required NPSH less than the available NPSH as shown previously. This would then conclude the basic presentation of NPSH. But we do have written material concerning this, a reprint, which covers other points, illustrating also the application of this chart to liquids other than water and to application for elevations as in Denver and other positions throughout the country. So if you would read this, go through the study of the material presented there, it will provide a complete and simple application presentation concerning NPSH, or not pumping so hot.